Hello back, everyone. This is Carlos Pimentel. Now I'm going to focus on the main technical aspects described in the patent with publication number WO-2024-136634 at the portal of the World Intellectual Property Organization, or WIPO, related to computational fluid dynamics and vortex methods. Now it is time to talk about the advantage of this specific vortex method. This numerical method is based solely on Lagrangian mechanics and conservation laws, such as circulation and vorticity, and avoids the use of fixed points in space to approximate the flow variables, except for the discretization of the object surface. Fortunately, the Navier-Stokes equation in their velocity-vorticity form provide a unique way to solve fluid dynamics by avoiding the pressure term. From this formulation, the pressure field can be reconstructed a posteriori via the stream function. But what's new about this development? Unlike other vortex methods, this one is based on a purely implicit vortex generation mechanism, which means that vortices are generated at the surface without any additional calculations related to fluid viscosity. In any case, the latter only plays a role just after the vorticity has been created by diffusing it to the surroundings. From this point of view, such a numerical method does not assume an attached flow condition at the surface, which inherently comes from a viscous motivation. This development gives the exact amount and orientation of the detached circulation vorticity from the surface, as occurs in two-dimensional well-tested vortex methods. Such a fully nonlinear approach is largely based on concepts proposed by previous authors, but extended to take into account flow separation on the entire surface, not just from some regions, leaving aside any kind of assumption. Once the three-dimensional full vortex cloud is released, it is naturally advected, stretched, and diffused by a vortex tube Porton scheme. Another novelty of this development is that it conserves both the total circulation and the vorticity at each time step, thus along the entire simulation, making it a perfectly stable method, even for long simulations, independently of the level of discretization. This feature is the most important, since theoretically, within a conservative case, all the total quantities must be conserved from one state to the other. From here, it is possible to propose more complex solutions, for instance, for non-conservative fields such as the viscous case. This table shows a comparison with the meshless vortex particle method, or VPM, and its improved version. Both of them are based on analytical solutions instead of a more conventional and straightforward finite difference scheme. For this reason, the particle approach requires additional calculations, for instance, to align the circulation to the vorticity vector fields in order to approximate a divergence-free field. It is important to realize that even the improved VPM version tends to be unstable for the conservative or implicit case, since it still does not preserve the exact total circulation for successive time steps, leading to instability as time evolves. Now it is time to talk about the patent document, which had been published at WIPO's website on June the 27th, 2024, after that the International Searching Authority of the United States Patent and Trademark Office, or USPTO, determined its patentability based on the three standard criteria: novelty, inventive step, and industrial applicability. The end date to enter the national operational phase is August the 9th, 2025. Because this patent describes fundamental aspects of a vorticity-based numerical method, it contains only a single independent claim, while the remaining two claims are dependent. The independent claim seeks to protect a fully nonlinear solution, initially justified for the steady-state case, where a total influence coefficient matrix, or ICM, takes into account the contribution of the full surface detached circulation. By analogy, for the unsteady case, the same principle is applied, but via the free vorticity contribution to the system of equations through the right-hand side vector. In any case, both ways are numerically equivalent. The full surface detached vorticity scheme allows for accurate calculation of vortex intensities and orientations, since circulations are obtained around and between all discretized surface elements. Therefore, a thought social scheme is more computationally expensive than a simpler one that detaches only one single vortex per surface element. It avoids additional computations for intensities and orientations and is the most accurate and straightforward scheme possible. To improve the accuracy of the calculation for the velocity induced by the object, the discretization of the body surface is done by dividing each bounded vortex filament into a set of bounded bottoms, originally represented by only one of them, while preserving the total volume, vorticity, and circulation. In addition, the dependent claim seeks to protect a precise nascent tube bottom approach, consisting of a first layer of vorticity released from the surface of the object, where the corresponding circulation and orientation of each element is obtained from the full nonlinear detached vorticity scheme. In the corresponding figure, 12 photons are released after the first iteration for a 2x2 discretization case. The first dependent claim seeks to protect a vortex tilting, squeezing, stretching scheme based on the conservation of both circulation and vorticity by allowing the variation of each released tube photon volume at each time step. Since this operation is quite complex in its implementation, it will briefly explain in detail next. In figure 16a, an isolated vortex filament marked with an arrow has its own vortex tube represented by a cylinder with its corresponding volume. Such a cylinder can be represented by a button with a spherical shape and the same volume. In general, note that the radius for the cylinder and the sphere are not necessarily the same. In figure 16b, the vortex filament has been advected from a previous time step under the influence of the total velocity field applied at each endpoint. In figure 16c, a new cylindrical volume is obtained based on a new vortex calculation after vortex squeezing or stretching between two successive type steps. Figure 16d shows a new equivalent spherical volume after pure implicit advection and vortex stretching. As expected at 2 times, the old and new vorticity volumes are different in order to maintain the conservation laws. Finally, in figure 16e, an additional calculation is performed to account for the vorticity variation via the fluid viscosity based on the core spreading method, which comes from a mathematically exact solution. In addition, its implementation is extremely simple and allows the vortex volumes to be increased over time. However, other viscous schemes can be explored, adapted and implemented to the present hybrid tube bottom scheme. The second dependent claim seeks to protect the numerical implementation behind the leading edge vortex wave contribution to the aerodynamic force, moment, and pressure coefficient calculations in the prestal region, where such an LEV remains attached to the leading edge by a counterintuitive rotation. Since the current computational method helps to describe the fundamentals of fluid motion based on a vorticity approach, a brief roadmap of its immediate future development is shown here. The first step is to extend such principles to the solution of fluid paths in air bodies in order to obtain a full nonlinear panel vortex method. After that, a fast computational algorithm could be implemented to improve especially the calculation of the induced velocity field, which is the most expensive task in the current code. The use of GPU parallelization could be explored. Optionally, a large eddy simulation or LES-based turbulence model, already applied in other vorticity-based methods, could be implemented. Theoretically, no turbulence modeling will be equivalent to solving a direct numerical simulation or DNS if the resolution is fine enough. This computational development can be exemplified within a pyramid, when its current state is located at the bottom part of it, and more complex aspects of fluid dynamics as compressibility and thermal effects can be solved in the near future as its development continues. This time I will talk about the disadvantages of the mesh-based solutions, but some of these can be exemplified by the pyramid behind. If you expect a more detailed explanation of the technical aspects, I encourage you to read the corresponding publications, consisting of a series of 3 journal papers. Alternatively, you can analyze the computational codes in Fortran language, which are available for download on github.com. See the comment section for related links. Thanks for your attention.